we are going to go over the formula that you see before you, F is equal to QV times delta B. So let's actually start off with that formula in written form so that we can reference it throughout the video. All right, so as you've heard from the last video, we are going to be doing the right-hand rule a lot with this unit, so the vectors are important. So the force is a vector, velocity is a vector, and of course that magnetic field is a vector. Okay, so as a reminder, the right-hand rule states that if we have two vectors, in this case A vector and B vector, okay, we have a cross product, and as a side reminder, right, we can rewrite this formula as Q V B sine theta, okay, and that equals to F of B. So what this shows you is the magnetic force that is experienced by a charge if it's in a magnetic field. But with this vector or its cross product rule, the important thing is that it's the perpendicular nature of the right-hand rule or the cross product that tells us the force. Okay, so because we'll be using the right-hand rule, I like to always color code all this. So this here on the force will be my resultant, which is my thumb. And then here we have the pink. This will be the velocity. This is my pointer finger, right? Because it's like, the charge is moving that way, right? And you jab your finger in the correct direction. And the B field will be the middle finger. Okay, so it's the field. The way that I can remember it is, if you stick your middle finger out, it's like you're saying like F you or like field you, B field you. All right, well, there we go. So those are the three vectors that we'll be working with. All right, so let me just finish highlighting that, and then we'll continue that. All right, so that's the formula. We're going to go into exactly what the formula entails, but let's go over the concepts first, and we'll do a couple practice problems with that right-hand rule. So here's a couple important things. In the previous video, using Biot-Savart, right, we said that if we have a moving charge, right, so this is charge and it is moving. If you have a moving charge, this charge creates a B field around the charge, right? So I'm going to just say it creates like a B field in a very 3D nature, okay, all around the charge. So this is the B field. Now, I'm going to put a subscript here. I'm going to call this the source, right, or the charge. This is the B field of the charge, okay? And the reason why I'm doing that is because if we see in the formula above, we see a variable for B in the B field, and it's important to know where the B field is coming from. All right, so we know that here this is the moving charge. We're going to call it the source. Actually, I think I like Q better, so I'm going to be using Q from here on out. And here's the other rules that we know. We have, so the north and north poles, okay, they will repel. This includes south and south, but north and south will attract. Okay, so those are the rules of the poles of the magnetism. But the important thing here behind all this is if you have two magnetic fields, okay, we will have a push slash pull, right? And that's either the repelling or the attraction. And a push or pull, this is simply what we call a force, right? So the reason why we bring this up here is we've already located one of the magnetic fields, and one of those magnetic fields is coming from the charge itself. So the mere fact that the charge is moving, right? So it has to have both of those requirements. The charge must be moving. It will create a B field surrounding it. And now we can actually discuss this formula. So if we take a look at that formula there, I'm going to rewrite it below so that we can add a couple of notes to it. What this tells us here, so this F of B is the force felt by the charge. Okay, so it's a magnetic force that is felt by the charge. And it's important to know that in future videos, right? So we know that if it's charged, it can also feel an electric force. But for now, we're just focusing on the magnetic force. Okay, and the force is felt by this charge. Okay, and of course, Q is the focus charge. But here's the other requirement: the charge has to be moving. So right here, if we take a look at this, if we have a focus charge that is moving, this will create a B field of the charge. So that's B field number one. And then we have the cross product, and we have that B. Now it's important. I'm going to put this as a subscript, but this is going to be from the outside source, okay, or the environment. So this is a B field that the charge exists within. Okay, important notes. So this is probably the more important notes. Not the same B field created by the charge. Okay, so now we have our two B fields. Our first B field is created by the charge for the mere fact that it's moving, and that charge, because it's existing in another different B field, right? So now you have two magnetic fields that can interact with each other. So if you have two fields that are interacting with each other, that's as if you just have two magnets that are being brought close to each other. Okay, and when you do that, the two magnets will interact, and the interaction is what we call a force. Okay, so this is formula. So one more time, as a reminder, f of b is equal to qv cross product b, where v is a vector, vector, and vector. Okay, so the reason why I'm bringing all of that up is one of the most common mistakes that students make is knowing where that B field is coming from. Right, is it coming from the charge, or is it coming from the environment that it's in? And the answer is from the environment that it's in. Okay, another little side note to remember: if you remember back from the mechanics days, we always say that you can't exert a force on yourself, right? So if this is a magnetic force, the magnetic field that the charge creates, right, that can't exert a force on itself. The field can't interact with itself. So it has to be something from somewhere else. Wonderful. Okay, so now let's get out our right hand and let's use the right hand rule. As a reminder, for the right hand rule, the thumb will be the force, the pointer finger will be the direction that the charge is moving, and the middle finger will be the field. Okay, so I'm going to give you several different examples. So the first example, let's say we are in a B field that's O. Okay, so we have a O field like so, and definitely copy these down. You'll see a lot of these types of problems. And let's say we have a positive charge. I'll do a positive charge like so, and it's moving in the rightward direction. So the question is, how is the force felt on this charge, right? What direction is the force? Okay, so if you have a right hand, remember, create that shape, right? It's like you're pointing this way, thumbs up, and your middle finger is off to the side. Okay, so make sure everything is 90 degrees. So my velocity is going to the right, so point your finger to the right. My field is going out of the page, and so at this orientation, okay, my finger is going into the screen, so that's the wrong direction. So out of the page, I'm gonna have to twist my finger around. Okay, so your middle finger should be pointing at your face, and don't hold this for too long. Just look at the direction of your thumb, and you should see that your thumb is pointing down. Now, I was like twisting and contorting my body, but just so you know, when you do these problems, like during like class time or during like a quiz or exam, right, your body doesn't have to stay stationary, right? You could twist your body around. So, for example, right, if I say up, I'm going this way, okay, I'm just gonna get up, and I'm like, up, the field is coming out, right? I could just twist my body so I can see that my thumb is pointing down. Okay, so make it easy on yourself. So the force is going down. Now, as a reminder, this is for positive charges only. If you have a negative charge, all you have to do is you have to just flip the direction of the force. So same scenario, right? Let's say same scenario, but we'll have there we go. If you have a negative charge that's moving in this direction, that negative charge will actually feel a force that is going up. So the sign has just flipped or reversed, or you could just use your left hand. Okay, but I prefer sticking with my right hand for the right hand rule. All right, so another one. So what if we have a B field? I'm trying to think of a. Let's see. Let's go this way. Yeah. Okay. So we'll do one that's easy on our wrists. All right, so we have a B field that's going to the left. Okay, and we'll have the charge. We'll have the charge going upwards. Okay? We'll have the charge going upwards, and it'll be a positive charge. So once again, the direction of the force. Okay, so get your right hands, make the classic shape. Pointer fingers pointing up towards the ceiling. Middle finger, B field, is going to the left. And now I can see my thumb is actually pointing at my face, right? So in this case, it is out of the screen. So FB is O. It is directed towards you. Okay. All right. So we just did two examples using right-hand rule. Now let's take a look at the cross product nature. All right. So as a reminder, sine of theta tells you the cross product nature of all these. So if we take a look at the previous problem that we just did, okay, we can see that the B field and the velocity vector here, what we get here is a 90-degree angle. So sine of 90 gives us 1. So if we take a look at FB is equal to QV cross product B, right? If we put a sine of 90 as a cross product, we get QVB times 1, meaning that we have, I'm going to just call it max force. So we have maximum magnitude of F of B. So that magnetic field is exerting all of its force on that moving charge. Okay, but what if this charge isn't moving at a perpendicular direction, but rather, so if this is like flat, rather, what if it is off at an angle? Okay, so let's say this here is angle of 30 degrees. So if it's off at an angle, right, the formula still applies, but now what you have to do is you have to put sine of 30 in there, which gives you a half. So if the charge is not moving perpendicular to the field, what you get is a reduced magnitude of the force. So here, your F of B would be a half as strong. Okay, so it won't feel as much force. So the important thing is, and by the way, if we take a look here, right? So if we look at a sine graph, here at the peak, this is 90 degrees. So at 90 degrees, we get a maximum magnitude. And we can see here at 0 degrees, right? At 0 degrees, we get no magnitude. Okay, so let's make sure that we see that and what that might look like. Whereas at 0 degrees, or even over here, this is 180 degrees, where that's 0. By the way, if this is 90 over here, the other side of the magnitude, maximum magnitude, this would be 270 degrees. And so in terms of a circle, this is 0 degrees, this is 90, right? This is 180, and here this is 270. Okay, so all that means is that we're still making the perpendicular nature, okay, where 90 and 270 are perpendicular, but 180 and 0 are parallel. Okay, so let's take a look at an example of 0 degrees and 180 degrees. All right, so we'll do the same example here where the B field is going to the left, okay, and this time the charge is also moving to the left. Okay, so make your classic shape. Okay, you're going to say, all right, so my pointer finger is pointing to the left, and then here, if you keep the shape of your hand, you'll notice there is no physical way for your middle finger to also point to the left. Okay, the only way that you can do that is by, making the velocity vector and the field vector parallel to each other. But remember, that breaks the nature of the cross product. Okay, you want cross product stuff to be at 90 degrees, but if they're parallel, okay, that breaks cross product. So therefore, here we can now say this is no force. Okay, so no B force. So no magnetic force will be felt by that moving charge if it's moving perpendicular. And this is because your theta is equal to 0 degrees. All right, let's flip it. What if that positive charge is moving in its opposite direction? Now, this is even more funky, right? So you have the charge moving to the left, but the B field is moving to the right, right? You can see that's definitely not 90 degrees, that's 180 degrees. So if your theta is 180 degrees here, right, we will still get no force. Okay, no B force. Right? So we have to make sure that every single vector is perpendicular to each other. Okay, and that includes the magnetic field or magnetic force vector there. All right. So the rule of thumb is the closer you are to perpendicular, the stronger the force will be. As you approach parallel, the weaker the force gets. All right. And I think that's it. I'll see you all next time. Bye bye.